Okay, so Kirchhoff's rules give us an approach for solving circuits that have batteries and resistors. But what if we have circuits that are different than that? What if it's not just batteries and resistors? What if we have something like light bulbs? All right, so light bulbs actually cause us a little bit of trouble because bulbs are not ohmic. Okay, so remember that when we use Kirchhoff's rules to solve a circuit, one of the key steps is we take every potential difference across a resistor and replace it with IR. So that tells us that we can't do that here because the resistance of the bulbs is not constant. It depends on the circuit. Okay, so while Kirchhoff's loop rule and junction rule are still true, they aren't going to allow us to solve it this time. So Kirchhoff's rules are not going to help here. Or at least not quantitatively in the same way that they were before. Okay, so how do we approach a circuit that has light bulbs in it then? Well, the first thing you want to do is color the potentials. Okay, so we want to take advantage of what we know about wires and batteries. Okay, so let's say I have a circuit like this, where I have a battery and then a light bulb, and then another light bulb like this. Okay, I want to know how bright are those two bulbs. Are they equally bright? Is one brighter than the other? So I'm going to name them A and B. And essentially, what I want to do is just color the potentials on the wires. Okay, so I don't know what the potential on this wire is, but I'm going to color it green. So this wire is green. Everything that's attached, all the conductors that attach to that wire, are at the same potential based on the rule for wires. Okay, I can do the same thing for the other wire. So this wire I'll color blue. Everything attached to this wire is blue. Okay, so what does that tell us? Well, remember the colors represent the potential. So the potential difference across A is from green to blue. And the potential difference across B is also from green to blue. So keeping in mind that green and blue are representing specific numbers, I just don't know what they are, that tells me that the delta V across A equals the delta V across B, which, for that matter, equals the delta V across the battery. Okay, so if it's our usual 1.5 volt batteries, then the potential difference across A and B is both 1.5 volts. All right, so what that tells me is if the bulbs are identical to each other, even though they're not ohmic, I still know they have the same potential difference, they'll have the same current, so that means that they'll have the same brightness. So same delta V implies same current, which implies same brightness. Okay, so in some cases it'll be easy to compare the currents through the bulbs. In some cases it'll be easy to compare the potential differences. So depending on exactly what the situation is, you'll want to use both of those tools. Okay, so let me do another one. Let's say that we have a circuit that looks like this. We'll have two bulbs still, but this time they'll be in series. Okay, so A and B. All right, well, if I do the same approach that I did a minute ago, well, I have some potential up here, and I'll have some other potential down here, and yet another potential in between. All right, so some other one over here. Okay, so I don't know how the potentials relate. I know that the potential difference across A plus the potential difference across B will add up to the potential difference across the battery. That's basically the loop rule, and we can also see that those two add up to from green to blue. But we don't know how it splits up. Maybe one has more than the other. What we do know now, though, is that the current is the same through each, because by the junction rule, any current that goes through A cannot get used up. It has to go through B as well. So A and B have the same current. which means same brightness. All right, so in this case, the potential didn't help, but the current did. In the first case, we couldn't use the current because we didn't know how the current split up, but we did know that the potentials were the same. All right, so let's look at a case where we can use both at once. Let's say we have, for example, maybe a circuit that looks like this, and then another one that goes like that. Okay, and I'll call this one A, B, C. Okay, so the first thing to notice is that B and C are in series. So any current that goes through B has to go through C. So B and C are going to be equally bright because they have the same current. There's nowhere else for the current to go other than current through B has to go through C. Okay, but how do we relate A to those two? Well, let's color the potentials. So if I color this wire some color, green, and I color this other wire some different color, blue, and then I pick a third color to go in between the bulbs, gray, well, then I can see that the potential difference from A, so the potential difference across A, is green to blue. And the potential difference across B plus the potential difference across C is from green to blue. So clearly there's a bigger potential difference across A than there is across B or C, because the differences across B and C add up to the difference across A. So what that means is that A is brighter than B and C, because A has more delta V. Which also means that there has to be more current through A. So more current went through A, less went through B and C, but there was no way to know that at first. We had to figure out that A was brighter because it has more potential difference, and then from that you could conclude that A gets more of the current than B gets. But that is not something that you can tell until you actually go through the reasoning. Okay, let's go through another example. So let's say that we have a circuit where we have a bulb like this, and then another one over here like this, and then a third one like that. Okay, so let's color the wires. If we go through and color this one green, every wire that's connected with nothing in between has to be the same color. And if I color this one blue, like that, and pick a third color for this in-between part, gray, like so, well, what can we conclude? Well, the potential difference across these top two, which I'll call A and B, this last one C, has to be the same. So the delta V across A equals the delta V across B. It's from green to gray in both cases. So same starting potential, same ending potential, they have to be the same potential difference across them. Okay, so A and B are equally bright. What about C? Is C brighter or less bright? Well, based on the potential differences, I can't tell, because I don't know how going from green to gray compares to going from gray to blue. I don't have any numbers. So I have to use a different reasoning for this. So what I'll think about then is the current. Well, some current goes through A and some current goes through B. But all of that current, both the current that went through A and the separate current that went through B, are going to join together to go through C. So the current through C is going to equal the current through A plus the current through B. So clearly C has more current than A or B, which means that C is brightest, and then A and B are equally bright. A and B are equally bright because they have equal potential differences. C is brighter because it gets more current than either of those.